And that is a great point on problem number one is, hey, how am I going to know where 72 degrees is? But I did give you a figure, a special figure called a pentagon. And it does say it's regular. Anybody want to just rehash all our memory and say, hey, what is a regular figure all about again? If a figure it's regular, all the interior angles and all the sides are congruent. So here's basically, in a nutshell, what I'm trying to tell you, because this is a regular pentagon. Whatever the degree measure is that you rotate E to P, whatever degree measure that is the same degree measure as if you go from P to A. As from A to T, T to N, N to E, etc. As I go from vertex to vertex, I'm rotating the same amount of degrees every single time. Can I get a little help maybe? Finding that degree measure I rotate from vertex to vertex. Well, if I go all the way around, how many degrees am I going? 360, all the way around, right? If E to E is 360 degrees, we all agree. That's 360. Now here's a little bit tougher question. How many rotations, how many turns would it take to get from E all the way back to E? If you count them up, there's 5, right? I got to turn this pentagon 5 times to get back to E. So wait a second. 5 times, I'm going 360 degrees, and they're all the same degree measure every time I rotate. 360 divided by 5, every time I go vertex to vertex. How many degrees am I going? Oh, look at that number I get out, huh? 72 degrees every time I go vertex to vertex. So this makes this a little less challenging now, doesn't it? Now that I know I go 72 degrees every time I turn it vertex to vertex. So if I start at point E, so I'm going to start at point E, 72 degrees. Is that clockwise or counterclockwise? Because I didn't write it in, but we should know by now. Counterclockwise because it's positive 72. Perfect. So if I start at point E, go counterclockwise, 72 degrees, that brings me to vertex. Make sure right there. Good. It'll bring me to vertex. Hannah, what do you got? Vertex? P. Good. Counterclockwise, right? So bring me to point P. So not too bad. I just got to figure out, depending on the figure, and I go vertex to vertex, how many degrees I'm going. Ooh, part B now. I didn't do 72 again. I did 216. Is that going to be an issue? If I go 216? Huh. Why is that not going to be an issue for me, Kyle?
It's divisible by 72.
Yeah. If you take 216 and divide it by 72, you end up with, hey, that's 3 rotations. Right? 72 and 72 would be 144, plus another 72 gives me that 216. So now somebody going from point P now, looks like I'm going to do 3 rotations from point P. And you would end up at 23. Luke, where do I end up if I go 3 rotations from point P?
N.
Point N. Good. Make sure, again, guys, going counterclockwise because it's positive. Everyone all right so far? Good? All right, let's go to a new figure. Let's go to an octagon. 8's up. Pretty clever, huh? 8 sides. Wow, look at 1 through 6. There's a whole bunch of degrees I need you to rotate, huh? Well, can we figure out first, like we did with the pentagon, can you guys help me out first as I go from vertex to vertex, how many degrees it is? So for instance, as I go from S to T, how many degrees am I rotating? Well, again, 360, right? All the way around from S to S. How many times would it take this octagon? How many turns, rotations would it take to get back to the beginning here? 8 rotations. 360 divided by 8, 45 degrees every time I go vertex to vertex. All right, 45 degrees every time. So let me do number 1 with you, and then I'll let you go on your own 2 through 6. So number 1, a rotation of G, 45 degrees. A rotation of G, 45 degrees. Where do I end up? Bless you. Emily, where do I end up? A rotation of 45 degrees at G.
Point I.
Point I. Great job. And then I'm going to give you guys a couple minutes here. Go ahead, 2 through 6. I'm actually very interested in what you guys are going to do when you hit 3 and when you hit number 4 in particular. Now I'm asking you to rotate a segment there. All right, let's, you guys are finishing up. Go ahead. All right, but here we go. Let's see what we got. First one up here. Here we go. Atticus, rotation, 225 degrees starting at U. Where do I end up?
I.
Yep. Hopefully, I don't know if you guys saw a little pattern between the first 3 of these, but hey, it happens every once in a while, right? Emma, how we doing?
Good.
315 starting at E. Also I, yep. And that's where it ends, kids. All right, what do we do with the segment, EI? Rotating the segment is the same as rotating the 2 points in the segment, 270, and seeing where you end up. All right, so if that was troubling, just rotate the 2 points in the segment. Where are we here? Lucas, what do we end up? 270 on EI, where do you end up?
S.
S? EI, it's a segment though, EI. Segment EI is rotated 270 degrees. So I need another segment back.
Sorry, I just haven't really understood. ZG.
Well, hold on. ZG is not a set. Well, ZG, EI was a side in the octagon, Lucas. EI, a side in the octagon. And we have discussed that every time I write.
GH.
Oh, Z's not a part of it. I don't know why Z's a part of it. Z's just Z is just the point I'm rotating around. I need an actual side of the octagon. Like EI, where I start, is a side. And now I'm going to rotate it 270.
GH.
GH. There we go. We got it now. GH. GH. All right, next up. Now I'm going to rotate S 135 degrees. What do you got for me? Vinny, what do you have?
G.
G. Yep, point G. And then, whoof, I saved the tough one for last, didn't I, kids? Real tough one there for last. Rotate ST 360 degrees. Oh, boy. Kyla, what do you got?
ST.
Whew, yeah, it goes all the way back to itself. Yep, ST. Good job. Questions there? Comments? Rotating. Something other than 90, 180, and 270. All right, next up, let's get off the degree measures here a little bit. And now, I want you to tell me the degree measure. So I have an equilateral triangle. You guys know equilateral. All sides, all angles are the same. I'm going to rotate it clockwise around the center. I need the minimum number of degrees it can be rotated to carry it onto itself. Before we find that answer, what does carry it onto itself mean? What am I talking about when I ask you to carry it onto itself? Quincy, what do you think?
Does it just mean to be in the same position as the...
I want the same, not the same, but I want another equilateral triangle back. So I don't want 360. There's something smaller I could rotate so I get an equilateral triangle back. So that's what I mean by carry it onto itself, is get an equilateral triangle back. Not the one I started with, but just still another equilateral triangle. And yes, 360 is an okay answer, but not here because I asked for the minimum amount of degrees, and there's something smaller than 360 I could do. So let's think here. Ooh. How many degrees would it take me to go from this vertex to that one? Because if I just go from that one to that one and turn it, it's the same equilateral triangle. Which is the same as if I just drew this in, this angle right here. Radhika, thoughts?
Is it 120 degrees?
How'd you get 120?
Because if you were to go the full way, it's 360.
Okay, turn it all the way around, Radhika, saying that's 360. And just like we've been talking with the octagon and the pentagon, how many turns, Radhika, is it going to take? Rotations is it going to take to get back to the beginning? 3, because it's a triangle, 3 vertices. So I take 360 divided by 3, 120. What's another, other than 360 still? Anybody find another degree rotation other than 120 and 360?
270 or 260, 240, sorry.
240, yes. 240 would also do it. 120, 240, 360. We could keep going up and up by 120s.
How does it, if you rotate it like somewhere in between like 90 or 0, like how does it then become not an equilateral triangle?
No, the one you are looking, I should have probably been clear on that, Sophia. The one you are looking at on your paper right now, in that same position. So here's what I mean. Let me get my equilateral triangle up here. So there's my equilateral triangle. All right, let me copy it. Move that over here. All right, so if I start rotating this, that's not the same thing I started with, right? I got to keep going. There it is. That took me 120 degrees. You're correct. It's still an equilateral triangle, but it's not the one I just started with. I basically have to be able to match them right on top of each other, which I would not be able to until I hit 120 degrees.
All right, I think I was confused by that.
Okay, no, that's probably, I should have discussed that a little more. I got to see the exact same triangle you are given. Other questions, concerns? All right, good job here today. Keep going with me. Ooh, now I'm going to take it next level on you. Let's rotate a line. You guys have a lot of experience rotating points. Can I rotate a line now? You're darn right I can. I can rotate a line. So I have a line, 2x plus y equals 1. And I want to rotate it 90 degrees. Give me the new equation of the line. Ooh. All right, can we start here? Can we just get this y equals? I'm not a big fan of when it's like this. What's up?
Y equals -2x plus 1.
Yep, I'm going to subtract 2x over. We always like it when it's in y equals mx plus b form, right? Always love that. Hey, I provided a graph too. I'm going to even throw that up on the graph. What's up, Sean?
Would be 90 degrees just be a negative reciprocal?
We're getting there. Yep, we are. You're absolutely correct. Let me throw this line up here right now. Here's 1 on the y-intercept. The slope is -2, so I'm going to go down 2 over 1, down 2 over 1. So here is the line right now we are trying to rotate. Rotate that line 90 degrees. And I know some of you maybe, you want to try to turn your paper like I showed you yesterday. That might be a good idea. All right, but the problem might be you're not going to know where your y-intercept is there because it kind of goes through, does it go through halfway, a third, a fourth? So I don't know if rotating your paper might be the best idea here for a line. But we can still get there algebraically. Here's how we're going to do it. The new line has to come in y equals mx plus b form. That's how I write equation of any line. And what are the two values we always need to write an equation of a line? Y-intercept and slope. Let's start with the slope first. And Sean just said it here in class. You are going to rotate this 90 degrees. So both lines, my original and my image, are going to form a right angle. What do I know about their slopes then? Negative reciprocals, correct. So these two lines, y equals negative 2x, which has a slope of negative 2, and my new line that I'm rotating are going to be negative reciprocals of each other. So what's the slope of my new line then? What's the slope of my new line going to be then? Got to be what? Kyla? 1/2. Yep. Slope of my new line, 1/2. Everyone at home, all right? I rotated at 90. They're going to be perpendicular to each other, which I already know from this unit as well. Slopes are negative reciprocals. Ooh, how do I find the B now? How do I find the y-intercept? Okay. How do we usually find the y-intercept? We take a point on the line and plug it in, don't we? A point we know is on our line, and we plug it in for y and x. I think you guys can do that. You can find a point on this new line. You got infinite points right now, don't you, on this line? Y equals negative 2x plus 1. Sorry about my 2. You got infinite points on there. Take one and rotate at 90. If you take 1 point right now on this line, rotate at 90, it's going to be on my new line. So you guys go ahead and do that because I'm going to ask somebody for a new point now. Take any point right now that's currently on the line I'm going to rotate. Rotate at 90 counterclockwise and write down what a new point's going to be. Okay, here you go. Maeve, you ready? What point did you pick from the current line?
1, -1.
1, -1. Okay, so Maeve took 1, -1, and you rotated it 90. Let me see if I can do that visually. I can. Yep. And then what did it become? What did it become when you rotated it? 1, 1. Okay, 1, 1. Yep. So I'm just going to jot down 1, 1 is on line M, the one I'm trying to put here. Everyone see where Maeve got 1, 1. If you didn't get 1, 1, fine. No, you could have picked another point. Use that point now. So now go back to y equals mx plus b. 1 is my y. M is 1/2. X is 1 plus b. Or use your point that you just found. Hey, I used a different point when I wrote my notes. Is anybody using -1, 0 now instead? That's fine. -1, 0 is on my new line. So let's finish this up. 1 equals 1/2 plus b. It shouldn't matter what line you got, what point you guys use. All of our y-intercepts should be the same. What are you getting for the y-intercept here? 1/2. Yep. It doesn't matter which point you use. Should have got 1/2. So finishing this up right now, line M. Y equals 1/2 x plus 1/2. Do you want to give it a check? I put it into Y1 and Y2, see if they are actually perpendicular. One is 90 degrees of the other. Now, could you have gotten away with it by turning your paper 90 degrees? I guess if you just assume that that was going to be 1/2 on the y-axis right there, I guess you could have gotten away, but you would have been playing with fire if it wasn't 1/2. Any questions?
Once you have your first point, you just use the slope to try and estimate. Like if it wasn't on 1/2, you could probably just look at the graph.
Yeah. And sometimes, even if you just turn your paper, you could figure it out. It just, this was a problem because that point right there, is it 1/2? Is it not? I don't know. But if that point would have went through at 1, we would have been fine. All right, couple multiple choices here to end the class. I got these from old Regents exams, if you're interested or not. All right, these came up on old Regents exams. Number 9 has nothing to do with rotations, but something we've done in the past already. So triangle ABC, it looks like I performed a line reflection. Doesn't matter what line I reflected through, it has nothing to do with the problem. So I took ABC, flipped it over a line, called it DEF. Then I took DEF and translated it. What's the relationship between my original triangle and my ending triangle? Think about what I did. You did a line reflection and you did a translation. What is the relationship between the starting triangle and the ending one? Thoughts? Thoughts here. Ooh, on fire. Maeve?
Should I say my answer?
I want to hear what you have to say, yeah.
One.
Congruent and similar, yes. A lot of people just pick congruent because they don't understand similar again. Similar! 2 triangles are similar. What do I know about corresponding angles? They're equal, congruent. Does a line reflection or a translation change angle measure? No, they do not. So those 2 triangles would also be similar. Good job.
How would something be congruent but not similar?
That's never happening. Anything that's congruent are similar to each other. Not in reverse, though.
Isn't it called like a dilation?
If I dilated, that would be similar but not congruent. Correct. But any 2 figures that are congruent are also similar all the time. Yep. And 10, let's go back to rotations. Everyone start with triangle ABG. Start with triangle ABG. Reflect it over line segment BG for me. So flip it over line segment BG. And then I'm going to ask you where you ended up. So there's my starting triangle. All right, after you reflect over BG, what triangle does it turn into? 2s. Hannah, what triangle does it turn into? GCB, good. So everyone, first step, reflect over BG, and it becomes triangle BGC. Next, rotate it 180 around point G. And remember, this is a hexagon. 180 degrees. So what triangle do I end up with after rotating 180? Emma, go ahead. When you're ready. Yep, you got it. There you go, GFE. And when 180 gets brought up again, because it's going to get brought up again, 180 degrees, what geometric term have we talked about that's 180 degrees?
Reflection.
Oh, in reflections, yes. I'm going way back in the beginning of the year. A line is 180 degrees, right? So you can just, when you rotate 180, you're really rotating on the opposite side of something. Okay? A straight line. All right, think about that way. When you rotate 180, you're going directly opposite where you are now. Last one. This one's a tough one, guys. I saved this one for last on purpose to go in the weekend on a strong note. This one is tough. Ready? So you got a rectangle, A, B, C, D. My multiple choice question here is which one of these will not, make sure you understand that, not carry it onto itself. Meaning, when I perform one of these transformations, I'm not going to get this rectangle that looks like this on your paper. I'm going to get a different looking rectangle. Which one will not carry it onto itself? All right, so let's go through the choices. Number one, a reflection through y equals x. Oh, all right, dig deep. You guys remember what was the rule for me? Y equals x. I think we even brought it up today. Y equals x, reflection. What do I need to do with the coordinates? Sophia, remember what I have to do with the coordinates for y equals x?
You have to switch them?
Switch them, that's it. Don't change the sign. Don't multiply by -1. Just switch them. So A would become what? 7, 1 would become 1, 7. Anybody want to tell me something about 1, 7? It's already there. So watch what happens too. 9, 3 becomes 3, 9. What do you know about 3, 9? It's already there. And if I do the same thing for C and D, am I going to get the same rectangle back? Darn right I am. So that will carry it onto itself. So not one of the choices I want because I'm looking for the one that does not. Everyone all right on why that one will? All right, now we get even tougher. Ooh, a reflection over the line, -x plus 10. Well, what's that line look like? Where do I start? What's my y-intercept? 10. I want to see what this looks like on the graph. 1, 2, 3, 4, 5, 6, 7, 8. Up right at the top. What's the slope of that line so I can graph a couple more points? -1. So -1, remember down 1, right 1. Down 1, right 1. Down 1, right 1. We get the idea. So I want, what happens when I reflect over this line? I reflect over this line. Where's D going? The C. Where's A going? Am I going to get the same rectangle?
Yeah.
Everyone at home? Yeah, I'm going to get the same rectangle, right? So that's not going to make a different one. So that's out. That's out. Uh-oh. Now let's go rotational 180. But now, hey, it's not around the origin. It's around a different point, 6, 6. So where's 6, 6 here? 1, 2, 3, 4, 5, 6. Right here. Here's 6, 6. And when you rotate 180, you're rotating the point directly on the other side of where you're rotating around. Where's C going to go if I rotate directly 180 degrees on a straight line on the other side of 6, 6? Where's it going to go? B. C is going to go to B. Where's B going to go? To C. No problems. You ready? Everyone with me so far? Because here it comes. Where's A going to go?
Somewhere.
Not to D, right? Because take a look. A would be somewhere 180 degrees is a straight line, so it's going to be somewhere over here. A prime is going to be somewhere over here if I go on the other side of 6, 6, 180 degrees. And the same thing applies to D, doesn't it? Okay, so that will not carry it onto itself. Because A prime and D prime would land on different spots. Go ahead.
How would I'm confused.
Okay, 180 degrees is directly on the other side. So if I get my graph out here, and I said, here is 0, 2, and I want to rotate it 180 degrees around the origin, it would end up right here at -2, right? Because this is 180 degrees, a straight line. So it ends up on the other side of the point you're rotating around. I got to rotate around 6, 6. So as I go from A to A prime, that's going to be 180 degrees because it's on that straight line.
Oh, okay.
Okay, it goes on the opposite side. I do not want to end this class just by circling 3 and saying that's great. I want to show you why 4 also works. All right, why does 4 work when I just change it from 6, 6 to 5, 5? Ready? So where's 5, 5? 1, 2, 3, 4, 5. 1, 2, 3, 4. See the difference here? Where's D? I flip it on the opposite side. I rotate 180 degrees, which is on the opposite side of 5, 5. Where's it going? And where's A going? See the difference between rotating around 5, 5 versus 6, 6. What's up, Kyle?
Is there a way you can do that, like mathematically?
You could use slope.
Okay.
You could use slope if I'm gonna. I could say up and over how many, up and over, match it. It still works. Yep. Yep. And if you did that with through 6, 6, you would have found it wouldn't have matched up. So, but yes, you could use slopes mathematically. Quick on the homework tonight. It's all in the packet, so you don't need to use graph paper. It's all in the packet. And beware, it is mixed review tonight. Mixed review. It is a good way to get ready for Tuesday's quiz. Mixed review tonight. It's just not rotation. All right. I'll see you guys on Monday. Quiz Tuesday, Wednesday. Have a good weekend. Behave.